Welcome to the Regents Physics Solutions to the Work, Power, and Energy problem set. Problems numbers 19, 20, and 21. We jump right in with 19 here. A rubber ball is dropped from a height of 1.2 meters. After striking the floor, the ball bounces to a height of 0.80 meters. A. Has the energy of the ball changed as a result of the collision with the floor? Explain. The answer is yes. We know that energy has been lost. We know this because it didn't return to its original height. If there was no loss of energy, all the gravitational potential energy at a height of 1.2 meters would have been converted to kinetic energy once it struck the floor, and then that kinetic energy would then be transferred back into gravitational potential energy as it rose to the original height of 1.2 meters. It did not do that, so we know that the energy had to have been lost during the collision. B. How high a bounce would you observe if the collision were completely elastic? The definition for a collision to be elastic is that there is no loss of kinetic energy. So whether you are elastic or inelastic in a collision is clearly simply whether or not there was a loss of kinetic energy. So to be completely elastic means there would be no loss of kinetic energy. If that was true, then it would return to its original height of 1.2 meters. And now that kinetic energy that wasn't lost would be converted right back into gravitational potential energy that it started out with. C. How high a bounce would you observe if the collision were completely inelastic? Well, to be inelastic means there was a loss of kinetic energy. Now, there's partially inelastic, and then there's completely inelastic. Partially inelastic means that some of the kinetic energy was lost, and to be completely inelastic means all of the kinetic energy was lost. You are familiar with these kinds of collisions to be completely inelastic when we did problems in our momentum study last unit when two objects stuck together. Okay, so that means there was total loss of kinetic energy. That means there would not be any bounce, and the height would be 0 meters. There would be no height gained back at all. Continuing on to number 20. If you drop a tennis ball onto a concrete floor, it will bounce back further than when you drop it onto a rug. Where does the lost mechanical energy go when the ball strikes the rug? Well, clearly what this means, applying the last question to this question, is that the collision was more inelastic with a rug than it was with a concrete floor. Taking a look at an equation that's on your reference table, we already talked about that total mechanical energy is the sum of kinetic and potential energies. And on the reference table we see that, but they've added this plus Q at the end. If we look up the value of the symbol Q over to the right hand side, it stands for internal energy. What this statement is, it's a true statement of conservation of energy, in that energy is the sum of potential plus kinetic plus any lost to the surroundings in the form of internal energy. So where does the lost mechanical energy go when the ball strikes the rug? It goes into internal energy and is used to do things like deform the spot on the rug, deform the ball. Some of it may go into heat. Some of it will go into sound energy. Okay, all those forms of energy are lumped together into a category called internal energy. So the lost mechanical energy is lost to the surroundings in the form of internal energy, of which forms would include the forms we mentioned. Lastly, number 21. An archer puts a 0.3 kilogram arrow into the bowstring. An average force of 201 newtons is exerted to draw the string back 1.3 meters. Assuming all the energy goes into the arrow, with what speed does the arrow leave the bow? And B, if the arrow is shot straight up, how high does it rise? All right, let's focus just on A for right now. Assuming all the energy goes into the arrow, with what speed does the arrow leave the bow? Let's take a look at what we've got in this problem. We've got a mass of 0.3 kilograms, force F of 201 newtons, and a distance 1.3 meters that the string is drawn back. Mass, force, and distance. And in A, they're talking about energy and asking us to find speed. Energy and speed, that's kinetic. Energy, force, and distance, dead giveaway that for A, we need to use the work-energy theorem. So we start with the work-energy theorem expression, W equals delta ET. We ask ourselves, what forms of energy are changing with the arrow? Is this arrow's speed changing? Yes. It'll go from rest to some speed we're trying to find. Is the arrow changing height in a gravitational field during the course of it being shot out the bow? The answer is no. And it's not attached to a spring in this problem. So our only change in mechanical energy is change in kinetic. In the next line, we make our substitutions. Work is force times displacement. Change in kinetic energy would be final 1/2 mvf squared minus initial 1/2 mvi squared for kinetic energy. So you can see that this is our change in kinetic energy expression. We now substitute the values that we know. We know the force is 201 newtons, its distance is 1.3 meters, and the mass is 0.3 kilograms. Vf is what we're looking for, it's squared, and the arrow starts from rest, so the initial kinetic is 0 since the initial velocity is 0. We go ahead and algebraically solve for Vf, and we should get to 2 digits, 42 meters per second. Now B, if the arrow is shot straight up, how high does it rise? In B, there's no friction, and while we know the force of gravity acts on it, okay, we don't know the distance over which that acts. We're trying to find a height, and so as previously taught, our first reaction here has to be that to solve B, we're going to use conservation of mechanical energy. So we start with our conservation of mechanical energy expression, EI equals EF. Our initial state is the moment the arrow leaves the bow. Our final state would be the maximum height that it rises. What forms of mechanical energy does the arrow possess in its initial state? It's moving, so we know there's kinetic, and we're going to use that spot as the base level so that H value is 0. It has no gravitational potential energy in its initial state. In its final state, at the peak of its flight, it's not moving, so no kinetic, and it's at a height above that base level where we shot it from in a gravitational field, so we know it has gravitational potential. So our conservation of energy statement becomes 1/2 mvi squared equals mghf. Note that in this case, the mass of the arrow is in both terms, so we can cancel it for ease of calculation. The initial velocity with which it leaves the bow is 42 meters per second as calculated in A. So 1/2 42 meters per second squared equals 9.81 meters per second squared times HF. We solve for HF and we get 89 meters to 2 digits. This will do it for 19 through 21. More to come as we tackle number 22 and number 23 in class tomorrow.